Oh, hello. Good morning, everyone. Today we saw LeetCode 236, lowest common ancestor of a binary tree. All right, given the binary tree, find the lowest common ancestor, or LCA. Given two nodes in the tree, according to the definition from Wikipedia, the lowest common ancestor is defined between two nodes P and Q as the lowest node T that has both P and Q as descendants, where we allow a node to be a descendant of itself. All right, so let's look at the first example here. Let's say node 5 was P and node 1 is Q. And we want to say, hey, what's the lowest common ancestor? Well, the lowest common ancestor in this case would be 3 because 3 is a parent of both P and Q, right? So hopefully that makes sense. 3 is a parent of both of these, therefore it's the lowest common ancestor. Let me show you another example. What's the lowest common ancestor of if P was here and Q was down here? I'll give you a moment to think about it, but the answer would actually be 5 because the problem statement says that a node can be a descendant of itself. So in this case, 5 is a descendant of itself, and we know that 9 is under 5, therefore the lowest common ancestor would be 5. All right, so now that you understand the question and what it's asking, let's go into what approach we use to solve this. I like to go with a depth first search approach. And what we're going to do is start at the root, and we're going to check the left or subtree, then the right subtree, and see, hey, do we find P or Q? And if one tree returns either one of those nodes and the other tree returns one of those nodes, and that means that they're split. So let me give you a quick example here. So let's say we're looking for 1 and 8. We'd say, hey, from node 3, DFS node.left, we go to the whole entire left subtree, and it would return nothing because none of these nodes are the nodes we're looking for. So eventually it will get all the way down to the bottom and just return null, right? So that means we know that the left subtree has no values that we're looking for. So now we have to go to the right subtree. So now we're at 1. We go DFS node.left. Node.left sees that we found one of the nodes we're looking for, so return up P. So from the left, we get P. From the right, we get Q. And that tells us that this is the split point between P and Q. So 1 is a parent of both P and Q because one's on the left tree and one's on the right tree. So the node we're currently at has to be the lowest common ancestor because this is where the split happens. If we went any deeper, then there's no way we can get to the other node. Let's say we were at 0 here. There's no way we can ever get to 8 because it's on the other side of the tree. So that's why the lowest common ancestor is 1. All right. So hopefully that made sense. And let me give you an example of us tracing it if we had to do it the other way. Let's say we're looking for node 5, so P, and 4 for Q. First, we go DFS node.left, and it would immediately find the 5 and return up the P to 3, right? We go DFS node.right. It would explore this whole entire subtree, and eventually it would just return none because there's no node that we're looking for here, and it would eventually get to the leaf nodes. So essentially, there's nothing here, and it just returns up none. None. Now, what does this tell us? If the right subtree returned none, that means there's no nodes there, and the left subtree returned 5, or P, for the node that we found, that means that the lowest common ancestor has to be whatever returned from the tree that had something, i.e. P, or 5. That would be the lowest common ancestor. We actually do not even have to go any deeper because we know that there's no other nodes that could possibly be the answer on the right subtree. So everything over here can't be the answer, right? And we came here. So that means we know that the next node we're looking for has to be underneath P, which is the node we just found. So Q has to be somewhere down here. We don't know where, but we know it's somewhere down here. Therefore, we could just return P. All right, and if you have any questions, I know that sometimes these can be a little bit confusing. Please comment down below, but we're going to get into the actual solving of the problem. So first, I like to zoom in a bit. Hopefully that's fine so everyone can see. The first thing I always like to do is say, all right, we need to take care of our base case. So what if they give us a tree with no nodes? I always like to take care of that first. So I'll say if not root, return none. All right, so if they give us an empty tree with no nodes, we could take care of that. Next, we're going to create our DFS function. So define function, so DFS, and it's going to take in a node. Next, as you remember, when we go DFS node.left, we want to traverse until we find either P or Q. But if we don't, we want to return none. So that's when we get to a null node. We want to return none. So our base case is when we run out of nodes in that subtree. So if not node, return none. All right. Now, the next condition we want to have is if we find P or Q, which are the tree nodes that we're looking for. So we're going to say if node equals P or node equals Q, return node. So that will return us the node that is one of the two nodes that we're looking for. So in this case, when we were looking for the 5, so in this case, when we were looking for the 5, it would return up 5 as soon as we go DFS node.left, because it's the first node that we found, right? In this base case here, we'll make sure that if we go DFS node.right, it would return null because there's no nodes on this right subtree that are the nodes that we're looking for. So we essentially cross them out. We know we don't have to search there. All right, so now we have to go left and right. Now that we have our base cases and return statements done, we need to go left and right. So I say left equals DFS node.left. And remember, whatever you go to the left-hand side, we have to do to the right. So DFS node.right. And make sure to change this to the name right. All right. So first, if DFS node.left and node.right both return something that is not null, then that means there is a node. One of the nodes we're looking for is on one side and another node is on the other side. Therefore, this is the breaking point or split point in between these two nodes. Just like if we were looking for 6 and 2, 5 would be the lowest common ancestor, right? Because this is the split point between both of the nodes we're looking for. So we have to account for that. So, well, if left and right, so if they both return truthy values, and the only way they return something truthy is if they have a node, we want to return node, because this will be the node that it splits off at, i.e. the lowest common ancestor. All right, but you might say, what if that doesn't happen? So what if left only returns true? Then that means that left is the answer. And what if only right returns true? That means only right is the answer. And if that doesn't make sense, make sure to go back to the explanation where I walk through. Hopefully everything will make sense. I don't want to go through that again. So we can say return left if left. So if left is truthy, we want to return left, else right. So it's just saying if left is the only one that's true, returns a node, return left. If it's not true and left is falsy, then we just want to return right, because this one checks that they're both not true. So we know at least one of them has to be. All right, perfect. All right, so now all we have to do is return DFS and the root, and hopefully it didn't mess up anywhere. Let's try this out. There we go. And we solved the question. It's pretty efficient. So I hope you learned something new here. And if you have any questions, please comment down below. I'm here to help you guys out. And drop a like if you learned something new. Peace.